Well, hello friends. Welcome back to Browser Hacking. Today we're going to continue reducing the memory footprint of Twitter because I feel like we got a whole bunch done in the last video, but there's still low-hanging fruit that we can go after. So we're going to do the same workflow where we run Ladybird and then attach the heap track tool to the web content process. We have to start Ladybird first so that the web content process gets launched, but now we're attached and HeapTrack will record all of the malloc and free activity. And then we will load up somebody's Twitter so that we can record some interesting activity. And last time we were able to knock off like almost 100 megabytes of the total footprint. I think it was 95.6 or something like that in the end, which was very, very nice. And I don't think we're going to be able to knock quite that much today, but still hopefully something in the double digits, I would think. So let's just let this thing finish loading here. I think it's probably good. Okay, and then we'll kill it. And HeapTrack comes up automatically. And we should be able to get a little clue here. So I learned last time that the place to look right away is essentially here, total memory leaked. And it's not actually leaked. It's just HeapTrack thinks it's leaked because we killed the process. I guess that's why it shows up as leaked. But because there is no corresponding free, I guess. But we have to go into the bottom-up view here to see what this memory actually is. So last time we focused a lot on shrinking AST nodes, and I think there's more to do here because as we can see, we got AST nodes near the top of the allocations, although the top one now is kmalloc array, which is essentially malloc. It's just a helper that takes like a size and the size of the element of the array, and then it does a multiplication safely so you don't get overflow. So this is used by our vector class in C++. So whenever you're adding stuff to a vector, the underlying storage for the vector is allocated with kmalloc array. So that's what we see here. So we got lots and lots of vectors of things. So we're going to drill into those. There's about 45 megs of vector storage to dig into. And we have about 33 megs of strings. Definitely also interesting. And then we also have all of these AST nodes. So you can easily recognize them because they're all allocated by the create AST node allocation helper. So I think basically we just have to pick something and then go look at it. So we did identifier last time, and I feel like we squeezed that one pretty hard. I don't think we ever looked at member expression, so let's do that. Okay, member expression. Hello. So how big is this thing? It is 56 bytes, and we have 193,000 of them. So there's value here. Like if we were able to shave, just one pointer off of that, that's 193,324 times 8, so about a megabyte and a half if you can get rid of just one pointer in this data structure. So member expression has an object and a property and a bool computed. Okay. So this boolean here is definitely wasteful. As you can see, it has 1 byte size, but then we're forced to put 7 bytes of padding because the size of the class has to be padded to being pointer aligned, basically. So it rounds up to the nearest 8 bytes multiple. So that's pretty sad. So 48 bytes, and then we spend another 8 bytes just for this Boolean. And expression is 32 bytes. So there's a thing you can do sometimes depending on the layout of your base class. In this case, I don't know if it will work. What you can do is if the base class ends in padding, or your superclass basically. So if your superclass expression here ends in padding, just like we end in padding here, actually maybe it's easier to demonstrate by just making a subclass of member expression. So if we had a submember expression, that would be a member expression. So we do this. Now, this thing will also be 56 bytes, just the same as member expression. And we could actually add more Booleans here, and it will still be 56 bytes because we're sort of they're sort of folding into the padding in the superclass. So the trailing padding here still has room for more stuff. So as you can see at the bottom, it says +6 padding. So one byte was consumed by this guy, and then we can still put 7 of these things here. Very scientific experiment here. So +2 padding, and the size is still 56 bytes. Eventually you will have more than 8 bytes altogether, and now it's grown to 64 bytes. So all of this to say that there's this neat thing you can do sometimes if your superclass has padding at the end. So the easy way to check for that, I guess, is to just move that up. And it's still 56 bytes. So our superclass does not have padding at the end. But what if it did? So we have to move this because we rearranged some things. That's okay. Okay, so now this fella is 56. Expression has no members, so AST node, and AST node is ref counted, so that, wait, ref counted adds a 132-bit member. And then we have these fellas. So that's 8 bytes, 4 bytes, 4 bytes. And we can see here, yeah, we're 28 bytes in. So we do have padding after the ref count in ref counted. And maybe we could do this. So this looks a little bit weird, right? But basically what we're doing here is that we're taking advantage of the fact that ref counted has one member, ref count type, which is unsigned int, so it's 32 bits. It has 32 bits there, and that means that we have padding in the end of the base class of AST node. Should I say base class or superclass? Base class just comes to me more naturally, so I guess I'll say that. Padding at the end of the base class. So we can fold another 32 bits in there. And this is now at offset 12 bytes. And AST node is 32 bytes. Whereas before, if we had the old layout, AST node is 32 bytes as well. What does that mean in practice? Oh, right, because now this one still rounds up to, it still has to round up so that we have a multiple of 8 total size. So if you look at AST node in isolation, we haven't achieved anything. But what we have achieved is we have now created padding at the end of AST node. So previously, AST node sort of filled up the entire struct, if that makes sense. And now there's 32 bits at the end that are not used. So This should mean that member expression is now 48 bytes. Yes, exactly. So if computed is at the end like it was originally, then member expression is 56 bytes. But because we have created a hole in the padding at the end of the base class, AST node, we can now stick mcomputed up front, and it will fold neatly into the padding, and member expression shrinks by 8 bytes, which gives us should give us that memory savings of 1.5 megabytes based on the number of member expressions that we allocate. So that is very, very neat. And also, this likely affects more classes, by the way. And I don't think there's any reason not to do this, because we're just rearranging the members of AST node. The only reason not to do this is it looks awkward, right? But for AST node itself, the total size of AST node is always the same. Yes, just catching up myself in my brain. Right. Yes, this is only ever good because subclasses can now pack better. Yes. Okay. So let's make a commit out of this. Let's see. Just my phone is showing notifications, but I'm just going to ignore those. Let's see, that looks unrelated. History. Okay, so we'll do the AST node change separately first. Rearrange AST node members. So there's a padding hole at the end. AST node inherits from ref counted, which has a single 32-bit member. This means that there's a 32-bit gap of 32-bit padding hole after ref counted after ref counted, where we are free to put something, or it will go to waste. This patch moves AST node mstart offset into that hole, into that padding hole. We now have a 32-bit hole padding hole, and we now have a 32-bit padding hole at the end of AST node instead. This will allow AST node subclasses to put things in the AST node hole by moving them to the head of the member list. Okay, so this, by the way, is it's a neat trick that I learned while working on WebKit, and we used it extensively in WebKit to pack various data structures. So it's an old favorite. So member expression. Yeah, so now we just move this fella, rearrange this fella right here, which will shrink it by 8 bytes. Also, just get rid of these. libjs. Rearrange, shrink member expression by rearranging members slightly. By putting M computed in the padding hole after AST node. After our base classes. In the padding hole after our base class, we shrink member expression by 8 bytes. Very cool. Okay. I guess we can do a quick retest just to verify that it actually worked out. Also, by the way, notice how we only have to rebuild 31 files now instead of 1,000 something like we did last time. Oh, shoot. I probably needed to rearrange something a little bit more. AST node.h. Where are we? AST.cpp. Yeah, I gotta rearrange these. But as I was saying, notice that we don't have to rebuild over 1,000 files just because I touch AST.h. So in the last video, whenever I would touch the AST header, we had to rebuild a lot. But since that video, I spent a bunch of time like shrinking the header dependency graph in libjs so that you can actually now touch the AST header and rebuild a tiny fraction of what you had to rebuild before. And I wish I would have done that before recording the previous video, but you know what they say about hindsight. So this one actually goes in the fix up hello. This one goes in the this commit, yes. Okay, now let's remeasure. So we once again heap track. There we go. And oh, a crash. That's not good. How did we crash? Oh, shoot. That was probably that browser history thing that I should have left alone. Right. It's that was a workaround for a crash that's currently on master that somebody's working on fixing. Right. Let's leave that in there and then try one more time. So previously we had 10.1 megabyte worth of member expression allocations. And also the total memory leaked was 236.9 megabytes. So let's see if we get close to a similar number or if there was more benefit here. It's a little bit unstable here because I think Twitter sends these client event XHRs, so we don't want to. It's always hard when you're testing with a live website to try to reproduce the same type of run. But in general, let's see. So what did we get? We had 236.9 before. Now we have 235.9. So we have 1 megabyte less, which is roughly what I was hoping for. I was hoping for 1.5, but you know, there could be instability from other things. So we can see we have the same exact number of allocations in member expression, but from 10.1 megabyte used to 8.6 megabyte used. So there's definitely there's just a clear progression in memory usage from that change alone. Okay, so what else can we look at? How about the next thing on the list, call expression? Maybe we can do something with that. Call expression. Okay, so call expression is 64 bytes. and it has a callee and then a vector of arguments. Okay. So there's definitely ways to make this smaller. One thing that I immediately notice is that call expression has a vector of arguments, but I don't think we ever like this is a parse tree, right? Or an AST. So we don't really need the functionality of a vector here. Like once you've parsed a call expression, the number of arguments isn't going to change, you know, because you're not changing the program after parsing it. So I don't think that needs to be a vector. And we could instead use something like a fixed array, which is one pointer plus heap allocation. A vector is 32 bytes, or 42 bytes. What am I saying? 24 bytes. I'm reading backwards. 24 bytes. So if we would change this to a fixed array, that would instead be, I guess I have to actually include that. So if that were a fixed array, it would be down to 8 bytes, putting call expression at a size of 48 bytes instead of the previous 64. So that's 16 bytes off, which would be 16 times 123,875. So 1.9 million bytes, almost 2 megs. So there's definitely potential there for savings. And you could go even harder, actually, and do something where you don't even allocate a separate storage, but you make a specialized allocation for call expression that has enough space for the arguments sort of in the tail of the call expression object, which would remove the need for the secondary allocation as well, because they would be fused into a single one. How are the arguments exposed here? Call expression. There's no API for looking at them, or there's protected. Oh, okay. So then, let's find out who actually accesses these M arguments. Oh, they're used internally here. Okay. Argument list evaluation takes a vector. What is a const vector? So we could probably just use a span instead. So what are those things? Argument. This thing also looks kind of sad and unfortunate, right? Because you're going to spend 8 bytes for this pointer and then another 8 bytes for the Boolean every time. There's obviously strats to shrink that further, but I don't think we need to go quite as hard to do pointer tagging and stuff like that. We don't have to. Let's not resort to that just yet. But it would be interesting to know how much memory we spend on this vector at the moment. So maybe we can see it up here. Actually, it is near the top. Call expression argument. So we have 8.6 megabytes in vector storage for vectors of call expression argument. That's quite a bit of storage as well. So by fusing together call expression and the arguments, which should be pretty easy to do because we just receive the arguments here at construction time. So we just need a helper to construct this. Yeah, so by fusing them together, we'll definitely use less memory, but it's not immediately obvious how much. So we just have to kind of test it out and see what kind of results we get. Let's look at, actually we do have to consider subclasses. So who inherits from call expression? New expression. All right, sure. So new expression is a kind of call expression. Sure. So I think in the parser where we create AST node new expression or call expression, we have to, oh, super call. It's not a call expression. Okay. So for call expression, we can just make a helper that creates it. It will be something like static non-null ref footer to call expression. Because this thing is going to get real small now, because we're 48 bytes, and we'll get rid of this pointer in favor of just having the arguments trail after the object allocation. So call expression will be 40 bytes plus storage for arguments. And then, yeah, that should be pretty good. Wonder how much we can save from that. Probably, I would think like at least 3-4 megabytes. We'll see. Okay, so what was I doing here? Create. And we'll take the constructor params here, like this. And yeah, we're gonna, no, this is okay, this is okay. We'll make a thing here, so call expression. Okay. And then allocation size is going to be size of call expression plus size of argument times arguments size. Very fancy techniques coming up. So we will allocate a slot for this by calling our friend Maluk. Okay. And then we will new into the slot. So we will new a call expression into the slot. And it will take the source range and the callee. And then we need the constructor, I guess, to absorb the arguments. And that will be done a little bit differently than what we had before. So we'll have to move this constructor out of line as well, but that will be okay. And I think this can just take a const, or even, why not just a span, honestly? Span argument const like so. Okay. What do you not like? I don't even know what it doesn't like. It doesn't complain. Maybe it just misses an initializer list. So m source range, m callee, move callee. And then for size ti in the distance from the start to the end of the argument's span. You don't like this because m source range. Oh, I have to pass that up to my base class, I guess. My bad. Okay, and then we do something like this. So m arguments is not going to be a fixed array like this, but instead it's going to be just a storage at the end here. Actually, maybe we'll reorganize this thing a little bit. Okay, and then it's not a fixed array, it's just an arguments storage with 0 entries. And then we use this technique in a bunch of different places in the system, by the way. So let's see if we can just do it this way. New. Can we do it? Argument. I guess we want to move the incoming arguments, actually. So better if they're not const, because then we can actually move them. So let's see if we can do things that way. Okay. Right. And then we also need to do the same technique for new expression. That also has to be a protected or even private, since it's a final class. And we need a create helper. So let's see. Hello. New expression. And not next expression, new expression. Hello. Well, this seems okay. We just have to replicate this thing. So we need the fancy helper. Just a new flavor of it. There we go. And then the constructor is more straightforward because it just has to call up to the call expression base class. So we can actually just do this, I think. Okay. And then finally, we need to teach the parser how to do this, because the parser can no longer access these constructors via the create AST node template. If you look at what this thing does, it's really just a dumb thing that news it and then gives it to you in a adopted non-null ref footer. So we have to instead do this ourselves. But that's not a huge deal. So same thing here. And if this compiles first try, that would be cool, but no. No. I'm missing too many things. Somehow I often think that things are just going to compile even though I didn't write half the code yet. So what are we missing? M arguments is missing. Sure, when we're in ast code gen, because we don't have a way to actually access the arguments anymore. I mean, we have M arguments, but we don't know how large that thing is. So let's make something like this. Arguments span, maybe. No, this thing is already diligent taking a span. So let's have an API that returns a span and call expression. So it will be something like, oh, and that makes me realize we need to know how many arguments we have. We got to store the number of them somewhere. So that's a great use of that padding we have at the end of the base class before our first member. So it should actually be possible to store it for free. Arguments span. Let's see. So the size of call expression right now is 40 bytes, not counting the arguments, trailing at the end, of course. And then we need to know how many arguments we have. So we need to store that. So we'll just say u32m arguments count. And this takes us from 40 bytes to 40 bytes, thanks to the magic of base class padding. Right, so the arguments span here then wants to return m arguments. Span m arguments, count. Wait, does this actually? You know what? Let's bring this out of line regardless. Call expression. All right. Would that be to your liking, Mr. Compiler? And then we're probably going to need to tweak more places. Yeah, of course. Of course. I should just show the errors here. Argument list evaluation wants m arguments, but it expects a vector. Let's make it expect a span. What's the worst that could happen? You don't like that, but what if I pass you the argument span? Wait, still doesn't like it? Oh, wait, this... Oh, it wants mutable argument span? Oh, I guess that's just an artifact of how the vector looked like. Well, we'll fix that. We'll just do this. There we go. Okay, so arguments span. Call expression create. Yep. And what's wrong with this function? Const. Too many const. There we go. Yeah, if I had to rebuild 1,000 files every time I was tweaking this left and right, this would be very cumbersome. Okay, so what else don't you like? Where are we? We are in parser CPP. All right. You want to hit me with an error? Nope. Okay. Parser. Are we actually in parser? Yeah, 144444. Okay. Wait, is this actually where we are? Void operator delete. Wait, what? Pointer used after so-and-so. Pointer used after void operator delete. It's complaining about a use after free. In what context exactly? The null literal constructor here? What? I'm so confused right now. Parse primary expression, and GCC is complaining about a use after free because it doesn't like the null literal, we're calling create AST node. So the null literal constructor on 1444, that's the one I was looking at, right? 1447, sorry. Wait, why do you say 1147? 1147. I'm getting confused. Let me back up. The right place to look is 1444. That's here. It's complaining that there is a use after free on a pointer to what? Non-null ref footer with TJS source code. Okay. I feel like GCC is wrong about something here, and I just tripped on something. This feels like some kind of diagnostic going wrong in GCC because I didn't touch this code. That's a bit annoying. Why are you so miffed about this? Okay, how do I paper over this problem? Am I making a temporary object? I guess I'm making a temporary, like here, I'm constructing something temporarily. So what if I just make that thing here? What is it that I'm making? I'm making like a source range. So what if I do this and then move it in here? Which should be equivalent to what we were doing before. So if this works, then something is up with GCC. Okay, so that does work. Just I have other errors. That's really weird. I don't know what's up with that. But let's not go down that rabbit hole right very now. So let's see, 4819. Oh, I gotta return the call expression. Return a dot ref. Maybe this is what I should do actually, like this. Yes. Oops. Okay, well, that was a whole lot of messing around. Let's see if it pays off. So I'll start Ladybird and then start heap track. Then we will go to the Twitters. It might be that we just screwed up the ability to run JavaScript. Yeah, we probably did. Okay, let's see. So I was moving these into place. One thing is I never destroy them correctly. So that's something we need to take care of. And it's essentially the same scheme as we have a string impl. So we do need our own, I guess we could have our own operator delete. Although technically I don't think we need to, since just a plain free will work. It's just if we want to pass in size information to k-free sized, we could do that. But more importantly, the destructor is not working, right? That's one thing. Okay, we should probably build just plain JS REPL so that we can test this. So we need a destructor for call expression, that's for sure. Call expression, because this fella needs to uninitialize, or it needs to destroy those arguments. So call expression. I mean, I guess technically we could also just do this. Slightly nicer. Okay. So I wonder why is this causing us trouble? We'll find out when we have a REPL so we can just test. But let's see, new expression plus size of argument times argument size. That all feels right. Don't send. Okay, almost there. So we need some kind of little test program just to perturb the call parser. So we'll just make a function foo that takes AB and returns A plus B. And then we'll call it with 1, 2, and then we will see what happens. I should probably have printed it out or something. Okay, let's log that. Okay, it doesn't print anything. That's concerning. Let's run Valgrind on it. Mismatched free? Okay, well that's a thing. Right, so we probably do need to override operator delete actually. But why doesn't the call do anything? We're setting up the callee. Oh, we're never setting the arguments count. That's what's going wrong. Okay, well, let's do that. Arguments size. All right, well, sometimes you forget things. Wait, arguments count. Maybe that wants to be argument count, actually. We'll fix that in a moment. Let's just, yeah, it works. Okay. And then let's make sure that we also override operator delete so that we don't get a mismatched new versus malloc thing. So call expression. Wait. This is a bit annoying. This is a little bit annoying because not all of these come in through malloc or through malloc like I'm doing it here. So if I have a generic pointer or I have a pointer to AST node somewhere. I call delete on it, but operator delete is not virtual. So that means that it needs to happen at the root of the class hierarchy. So this fella needs some special handling here, right? Because you can't virtualize operator delete, can you? I feel like you can't. But operator delete, is that a thing? I don't know. I don't remember these things. Virtual operator delete, you can't explicitly declare it. Right, it's static because all it gets is a pointer to something that it wants you to delete. So, what's the strat? I guess the strat is to, we don't have to use new here. We can make it symmetric by just always using malloc. So we can fix it that way. Size of t, and then we just new into the slot that we just allocated. And once we do that, then we are free to implement our own thing here that just does wait, do I need to do that here, by the way? I just need to free it, right? I don't need to invoke the destructor. Yeah, C++ does that for me. It's been too long since I wrote a custom delete operator. Free putter. Yeah, no big deal. No sweat. So if I do this, will everything just work now? We'll find out. Okay, that works. Will I get complaints if I valgrind? Mismatch, free, delete, delete. Dang it. Okay, what don't you like now? Operator delete. Bum 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 bum. Allocked and parse program. Oh, parser.cpp line. Maybe we have a custom thing happening on 492 here. Yes, here's a custom one. This one does not use create AST node. We can switch that up. Make sure that it allocates it consistently. There we. Wait, what do you not like here? Too many parens. All right, all right. This should be clean now. Yes, clean, lean, mean washing machine. So let's see how it fares. Are you mad about one of these things again? Pointer used after operator delete. Now what? These are so weird. So where's it now? Parser 1445. It's the same exact place where it was upset at me last time, but now my workaround is in place. You don't like it? Why not? Create AST node. What if I move it like that? And like, does that matter? Are you gonna like it better now? This is like one of the most annoying things when you don't really, yeah, it liked that, okay? So, I don't know why I was upset about this. Yeah, when there's something where like, you hit the TV and the picture becomes very clear, that's a bit annoying. So can we finally see if this works and what kind of gains we can get from it? So before this change, we had 235.9 megs total leaked, and we had call expression. We had 7.7 megs worth of call expression. And we also had the array of arguments here, 8.6 megabytes in that. So we'll see how these changes affect the total usage. Okay. So let's look at the summary first. So from 235.9 to 221.1. Hey, look at that. We are down about 14 megs. That's very promising. So what were we looking at? Call expression, right? It's right here. So it's 7.5. But keep in mind, call expression create now does the entire allocation, right? It no longer has a separate vector storage. So that's 7.5 total versus what we previously had, which was 8.6 plus, that's 8.6 vector storage plus 7.7 objects here. So 14 seems like a bit much of a diff. So maybe there's some other instability here, unless we also had new expressions, I guess. I don't see those anywhere near the top. Can you filter here? N-E-V. Okay. They're probably here somewhere, but I am just blind. Oh, here they are. Yeah, that's not many. There's like 2,000 new expressions in the code, so it's not that. All right, well, still, that was clearly profitable. It allowed us to, at the very least, consolidate those two allocations, shrugging off about 7-8 megabytes. Very, very good. So the downside to these changes are that they introduce a bit of complexity, right? But I think it's complexity worth taking on, because there are, I would say the new object style is nicer. You know, we have a perfectly sized object that has just enough space for the things that we need to store, no extra padding or extra capacity for appending more arguments, because we're never going to do that after parsing. And yeah, it's like we're going from like kind of a mutable parse nodes to immutable fixed size parse nodes, which is really good. And the shrinkage, of course, is very, very good. But it would be lovely if there were sort of a better pattern for encoding this type of stuff, because I think we're going to probably do the same basic concept for more nodes. And it would be cool if, you know, if there was like a reusable way of doing this without writing all that extra constructor-destructor logic. But I guess the trick is that you're always dealing with like slightly custom scenarios. So it's not like they're all going to be exactly the same. So we'll see. We'll see what we can come up with. Still, this is very, very promising. So let's try to turn this into some kind of commit. Just going to get rid of some of these windows. Too many windows. Too many windows. Okay, so, well, the thing I don't like now is the weird hacking I did in the parser just to try to sort of quiet compiler thing. So let's see what happens if I just undo those changes. Will it still compile? If I just undo those, will everything still just work? Because then I'm leaving them undone. And maybe the real trick to getting that working was just to do a move here when we're creating the AST nodes. Maybe this is enough to placate the compiler or satisfy whatever the heuristic thing is upset about, which we don't even know. So, okay. That's good. That's good that we don't need that change. So let's see if we can... Oh, I didn't actually end up using fixed array, so we don't need fixed array. That's muy bueno. I didn't use it, right? Yeah, I didn't. Super cool. Okay. Maybe we should do a quick smoke test with test.js also, just to see that I didn't totally break the world. I mean, the fact that we could load Twitter without complaint is a pretty good indicator that JavaScript is working, but it's good to run the test suite as well. Okay, we seem to be fine. So let's take on some changes here. So the first change I guess we can take on is create AST node. And the custom operator delete, and then the change for symmetry inside the parser where we allocate the program node as well. We'll take those, libjs, allocate, use malloc and free for AST nodes. This will allow some AST node subclasses to allocate extra size, some extra tail size for data storage. Coming soon in a subsequent patch. Okay. And then we have some weird nonsense formatting changes here. I don't know what's up with these. What on earth? What on earth are these? I didn't touch any of that, so just discard that. And then let's see. Maybe instead of calling it arguments span, I should just call that arguments. Argument span. I can just call it argument. And then we'll call the member argument count instead of arguments count, just for fanciness. Arguments span. Yeah, arguments just looks so much nicer. Yes. Yes, clearly. Obviously nicer. Yeah. Okay. Git commit libjs store call arguments make one compact allocation for call expression and its arguments. Instead of call expression storing its arguments in a vector of argument, we now custom allocate the memory slot for call expression and its subclass new expression so that it fits both call expression and its list of arguments in one allocation. This reduces memory usage on Twitter AwesomeCling by what was the exact number? Not going off of the total here, but if we just look at how much we save if we calculate ourselves. So we had 7.7 megs in the call expressions plus the arguments 8.6. So using the back of the envelope calculator here, 7.7 plus 8.6, that's 16.3. And then in the new version, that is all covered by 7.5 total, which is just absolutely sweet. So we have saved 7.5, 8.8 megs. That's really nice. Okay. Yeah, and then there's that history workaround. Okay, so what else can we look at? What comes next after call expression? There's object property. Let's see what's going on with that one. Object property is 56 bytes. How many did we have? We have about 105K of them, 106K. 56 bytes. And okay, so we have a situation, looks like here we have some smaller values near the end, 4 bytes of type and 1 byte of Boolean. And the type is pretty restricted in possible values. So I think we can confidently rearrange here. So 56, by just shifting these to the front, it's still 56 at this point, but if we say that this one fits in a U8, at that point it becomes 48. So we save 8 bytes. And that's 8 bytes times 106. So about 800K. Easy peasy. So that one we can just take. So we just need to rearrange these fellas so they go up front. And will it just work? I think that will just work. Yeah. Shrink object property AST node by rearranging members. By putting smaller members in the padding hole after the AST node base class, we shrink object property by 8 bytes. Cool. What else? Object expression. What's going on with you? Object expression. That's 120 bytes each. Oof. And we have 43K of them. So it has a vector and an optional source range. 120 bytes. So both of those are pretty hefty things. Optional source range is that's pretty heavy. So optional adds a pointer, and then source range itself is like 56 bytes. So what is the size of this thing now? It's 64 bytes. So we could probably shrink that down to 8. Because if you have an invalid property range, which sounds like something that's kind of rare, if we just use an ohm-putter for that, we already take it from 120 bytes to 64 bytes. So like almost cutting the size of this thing in half, which should be able to give us a more than a 2 megabyte reduction just from doing this. So let's try that out. We just have to change some of the logic so that it has an ohm-putter instead. Optional is it's not the most space efficient thing, because when you have an optional something member, you have to allocate that member becomes the size of the T inside the optional T plus the flag for optional itself to know if the member is present or not. So I'm guessing we need to look in the parser for where this is set up. Object expression, yeah, invalid object literal property range. So we'll just use an ohm-putter for this. And instead of has value, we just use a null check because it's now a pointer. Here we have to use make so that we create, not source code, source range. Can we just do that? Yep. And this is just a plain pointer at this point. A pointer at this point. Did that work? Wouldn't that be nice if that just worked? Seems almost too easy. Test.js. Okay, well, this runs. So I'm thinking, yeah, that will probably have cut it down pretty well. And at that point, we should be down to like 2 point whatever. We had 43,388 before. 43,388 instances of this thing. So if it went down from 120, which was the previous size, so 5.1 megabytes, that adds up. So if it's now 64, it means that we are 2.7 megabytes. And at that point, I would say let's not get fancy with custom allocation schemes just yet on this particular node. I think the other one, there was a lot more to save because we had far more of them. So let's just do this one change for now. We'll leave some money on the table here. Okay, so this object expression libjs use ownPutter instead of optional, or shrink object expression by using ownPutter instead of optional. Yes. For the by using an ownPutter source range for the invalid property range. I'm just gonna put this in quotes is what I'm trying to do here. Invalid property range. We shrink object expression from 120 bytes to 64 bytes. That's really nice. Let's see what else we had going on here. Function body. What's in that function body? These properties, by the way, we could pack them in probably. Actually, you know what? I'm just going to see if we have a ridiculous amount of this object property right here, this vector. So there's 1.6 megabytes in storage for those vectors. So it's much smaller than what we saw with the call arguments. So let's put this one on the back burner for now and look at other opportunities. So function body was another one. Function body is 136 bytes, has a single thing in strict mode, inherits from scope node, which has a whole bunch of vectors, actually. I see. Scope node has a bunch of things because it has multiple vectors. Each vector is 24 bytes. Okay, these are pretty chunky. This kind of scheme is it's less straightforward because you can't just like easily put them all after. I mean, you can, but then you also need to keep track of like where each section starts, and then you're sometimes you're dealing with like different sizes of the things you put in the tail and things like that. But let's just jump over this one, look ahead a little bit, look for some low-hanging fruit. I want some slightly lower hanging fruit. It's a variable declarator. 56 bytes. Has a variant and an init expression. What about numeric literal? This one just has a value. Value is 8 bytes. On top of literal is 40 bytes. So literal doesn't do anything fancy. Yeah, so that one is already pretty well packed, actually. Identifier we looked at last time. What about function expression? This fella is 96 bytes. Has no members of its own, but it inherits from expression and function node. Ooh, look at that. Multiple inheritance. Function node looks a bit chunky. So how big are you? You are 64 bytes. And there might be some opportunity here to at least do some super cheap rearrangement and save a little bit of space. What is a function kind? Function kind definitely fits in a U8. So you get to be a U8. And then maybe we should start a rebuild already in case that changed a lot? I guess it didn't. So 64 bytes still. Function kind is now 1 byte. And these are all 1 byte. So we could, hypothetically, what if I just did some sneaky trickery like this? Would we suddenly fit in a smaller slot, I wonder? So, some bit fields. Does that make us smaller? It saves us 8 bytes. Okay, okay. Are there any downsides to doing that? Doesn't look terrible. What was the count of these things? It's 24K of them. 24,000, if save 8 bytes, that's like 190K. It's not nothing, but it's like, well, it's not nothing, but it's also like, why not take it? It's free, free money, basically. Yeah, so let's say libjs, make function kind enum 1 byte, a u8. Yes, let's just make it a u8. And actually, just for clarity, let's say make the function kind enum class a u8. Okay, and then do we need to rearrange anything? That's 4 bytes. Yeah, you could do schemes here with parameters at the end and a trailing allocation and stuff like that, but that's harder when you are part of a multiple inheritance configuration. But since there's 8 bytes of money on the table, let's take them. libjs shrink function node by 8 bytes by using bit fields, I guess. In fact, did we need to make this thing a bit field in the first place? 56 bytes. Yeah, it didn't need to be a bit field. It's just, let's only do these. I don't need to mess with this fella. By making the Boolean members be bit fields, we shrink function node by 8 bytes. By a total of 8 bytes. Just to make it look a little nicer in the commit. Okay. I was starting to scrape a little bit here. Sequence expression, binary expression. Oh, wait, I jumped over string literal before. Totally skipped over string literal. What about string literal? Maybe string literal does something stupid. Well, this looks stupid. Why is there a Boolean at the end here called isUseStrictDirective? I guess parse nodes know that they are a use strict. This seems to only be used inside of the parser. So, wait, who sets that? It's set up at the construction time. Okay, so when we construct these, we say use strict. Okay, let's see. Is use strict directive. We just check if it's a normal string literal and the value is either use strict or use strict, and as a single quoted or double quoted string. Is that the whole thing? That feels like something that we could just figure out at any time by like looking at the string? Like, why do you need to cache that information? Like, can you just compute that the one time that it matters? Or where does it matter? Where does it matter? If string literal is use strict directive, okay. Let's see, so we're iterating parse directive. So we're checking if we parse a statement, we check if we get a string literal expression, and then we check if it is a use strict directive. The thing that gives me pause is this fella right here. String literal type has to be normal, and it could also be non-tag template or tag template. So it's not like painfully obvious to me that there isn't some template situation here to consider. So I'm not going to get rid of it entirely, but we can. Maybe it's possible that we could just get rid of it entirely, but at the very least, we should be able to just rearrange it quickly from 48 bytes by just doing that to 40 bytes, 48 to 40. Yeah, so saving 8 bytes per each, which there's actually 2 separate things here that allocate these. It's kind of funny, depending on the, if you're initializing it with a string view or with a string. So we have 96K plus 88K. That's actually quite a bunch of them. So 96292 plus 88733, that's how many we have. 185 total. Times 8 is about 1.5 meg. So definitely worth just doing that little tiny rearrangement there. And yeah, it is, if it is possible to not have this at all, that would be better, because that would give us another 1.5 megs or whatever the number was. But yeah, since it's not immediately obvious, I'm not going to spend time analyzing that right now and risk messing something up, but instead we'll just do that little tiny rearrangement there. libjs shrink string literal by rearranging its members by moving the is, or what's it called? What was it called? Into the padding at the end, padding hole at the end of the base class, we shrink string literal by 8 bytes. Yes. Cool. I feel like we've done like a whole bunch of ones now. I wonder where we're at in terms of let's do a new test run. So let's see. Because now I'm kind of curious where we are compared to where we started. Wait. Okay. Did I lose my internet connection? Wait, what? I got the packet when I control seed. That's suspicious. What the heck? Okay, let's try that one more time. Yeah, okay. I don't know what that was. Now it's loading. So where did we start? We started at 236.9 total leaked here. Let's see where we are currently. Okay, got those 2 client events. We break. And then where are we roughly? 223.7. So we are down from 236.9 to 2237. Yeah, so I think that's a more honest one. We had like 221 at some point, but I don't think that was correct. 2369. Yes, that was the first one. 2237. So we're down about 13.2 megabytes since when we started. That is good. That's good. So let's see. This is the latest, and this is the next to latest. And wait, what are you? You are the first one, right? So if we just compare to the first here, when we started out, we had member expression, which originally was 10.1 megs. Now it's at 8.6. We had call expression at 7.7 plus vector storage. Now at 7.5 total, including vector storage. We had object property at 5.8, down to 5.0. Object expression at 5.1, down to 2.7. Very good. String literal at 4.5 plus 4.1. String literal. Wait, they're exactly the same? Wait, am I looking at the right thing here? This is the very latest. String literal. Did I not just shrink string literal? Did I mess something up with that? 40 bytes? I wonder if malloc has if it's the case that malloc has a 48 byte size class but no 40 byte size class, then maybe when I ask for 40 I still get 48, which would be sad. Because it means that and if that's the case, then it means that I'm not getting anything like I'm not getting any actual savings from this. That could be the case. That's often the case, that malloc has like these specific sizes that it hands out. And not every multiple of 8 is, not every increment of 8 bytes is represented in the sizes that it will hand out. So that would be a bit sad. And all the more reason to investigate if this use strict active thing is something we could compute on the fly. What else did we do? Function node, right? So that was function expression. Was part of that, right? So we're definitely in better shape, but I feel like it would be cool to get like some bigger chunks here. What can we go after? So we have that scope node thing that I didn't dig into, because it had 4 vectors. And who was the scope node? Somebody was a scope node. Was it the function body? Yeah, function body was a scope node. But I wonder about those vector storages. Like, how much are we spending on those? This is a vector of statement and of declaration. It's not that much, actually. Vector of declaration. Statement. What about these? Declarative environment. Maybe we could be better at computing if we compute the exact amount of space that we need. I wonder if that's something we could do better. So declarative environment binding, these look pretty chunky. We have 12.4 megabytes in these vectors. What if we could let's go make sure that they're perfectly sized, because as you can see here, we're growing them with appending. And when we append to a vector, we will, we don't grow them to like the next exact needed size. We add a bit of padding at the end so that the next append doesn't have to allocate, right? But if we were to, if this is a scenario here, I think it is, when we're performing a function call and setting up the bindings inside the function, we know exactly how many binding slots we need in that vector. So it should be possible to allocate the exact size of vector storage that we need instead of appending, growing as we go. So that it could be both faster and more space efficient to do that. So let's go take a look at function declaration instantiation. When we're talking about it's actually declarative environment, create mutable binding. That's doing the append. So create mutable binding. Yeah, this fella here is appending. And it's declarative environment. It will just do an append. Yes. Can these be packed? There's 8, 8. It's kind of screwed. It's 8 bytes, but due to alignment, we can't really shrink it any further. We could have a capacity setup call. So what if we're dealing with declarative environments here, what if there was an API that was something like ensure capacity that we could just call beforehand? This is analogous to our vector ensure capacity thing. And this would simply make space in the underlying vector. So ensure capacity, needed capacity, like that. Let's see what happens if we do this. And then we need to figure out how much capacity to ask for, because if we have the right amount of capacity, append will just use that capacity but not allocate. So we should be able to ask for the exact size needed instead of discovering it and accumulating padding. So let's see, environment, create mutable binding. Are there multiple of these? There are. How can we learn the exact size? Here's more. That's kind of irritating. So I don't really want to make a big ugly loop here at the top to calculate how much space we need. I mean, we could, but that would get so grungy. What would be another option? I guess, we could do a little bit of okay, so let's say that I don't do this because I can't compute that trivially. But what if instead, just as an experiment, at the end here, what if we had an API that was something like shrink to fit or whatever? So it will sort of get rid of any excess capacity because we're not going to put any more bindings in. We might in the future, and then it will use append, of course, if you use eval or something like that. But as an optimization to like get rid of excess memory usage, if we had that API, and then we could call that at the end of function declaration instantiation. So what is it? Environment shrink to fit. Let's see. I wonder, I guess I have to check if it is a declarative environment. Yeah, it's a little bit janky, but let's move forward. So if the lexical environment declarative environment, something like that, and we'll do it to the var environment as well. And if it's not the same as the lexical environment. Or we don't have to get fancy. That's a no-op in that case. Okay, so if I do that, and then what would shrink to fit actually do? I guess, well, we could log here, like, just out of curiosity, like, what's the size versus the capacity? So STF, size, capacity, just to see if there's like a big difference between the two. How much size do we have versus how much capacity for bindings in this environment object? And just as a test run, let's just go to Twitter just to get some random data coming up. Okay, so it looks like it's fairly common that there's almost double the capacity compared to the size. So there seems to be potential for savings here. Like, I mean, we did a very small sample here, just like eyeballing it, but you add 1 and you get capacity for 5. That's definitely wasteful. So, how do we shrink this thing? I guess one thing we could do is something like vector binding shrink wrapped. This will just be a hack just to test it out. Shrink wrapped, ensure capacity, and we'll set it to the binding's size. And then shrink wrapped. I guess we will have to reappend everything. So binding and bindings. What if we do that? Move them all over and then shrink m bindings move shrink wrapped. So now, after we do that, then they should be very tightly allocated. Let's see if that actually works. We should see size and capacity being the same instead. Okay, yes, that does work. Okay, so it looks very stupid, but let's see what it does. And if this is very helpful, then we can come up with something slightly nicer. Okay, so we are running here, and while this loads, we can look at, so this is what we're targeting. We're targeting this vector of declarative environment binding, of which we have 12.4 megabytes of vector storage in the last recorded run. So there's 1.8 million of these vector storages. Quite a bunch. 12.4 megabytes. Let's see what we can get it down to. Okay. 12.4 versus dun, dun, dun. 6.8. All right. Definitely less. That's very cool. And yeah, as you can see, the number of allocations that occurred has increased, but the amount of storage has decreased. So we'd have to do a bit more work to shrink the vector, but the end result is that we use quite a bit less memory. So from 12.4 to 6.8, 5.6 megabytes saved, definitely not nothing. And we're down to 216.1 from the original 236.9. So now we're down about 20 megs from where we started. Getting close to 10% total reduction. We would need to go a bit further, but I think, let's see. What we would really like to have here is just a shrink to fit API in vector, basically. So you could just say bindings, shrink to fit, right? So what if we just add that API? We don't have to do it in the most beautiful way, but what if it just knows how to do that? So we have a resize API. We have ensure capacity. I guess this is sort of related to resize, actually. So resize, shrink to fit. Okay, let's implement this in the stupidest way right now. So if size equal to capacity, return. Otherwise, vector new storage, new. And then new vector, ensure capacity size. For auto element in this new vector, uncheck depend. Because we know it has enough capacity, we don't need to check with every append if we have to grow. So we append element, and then at the end here, we just say this, oops, move new vector. Yeah, this can definitely be nicer, but I think that's pretty cool. This will be a big repo. So let's eat that. Yeah, this can definitely be nicer. It can do I'm sure it can do this in some smarter way to avoid some amount of work. I just I'm a little bit too brain drained to know exactly how to make it better. So we'll do this dumb version right now. We can just shrink to fit the vector. And I bet you that we can shrink to fit a whole bunch of other vectors as well that we see here. Now that we have such a tool. So let's see. Let's do some commits. Oh, dang it. It's doing a bunch of silly white space or formatting changes again. Yeah, some discrepancy between Clang format, I guess, between CLion and my local Clang format. I'm just gonna say commit add vector shrink to fit. If there's more capacity than size, the vector is reallocated to have capacity size. Yes, this spends a little bit of CPU, but reduces the amount, a little bit of CPU on the effort to rearrange things. In exchange for, we don't need to say that. That's okay. Okay, we still have a bit of building to do, but it's not that bad actually. Okay, so shrink to fit, and then we're using shrink to fit. Libjs shrink clarity environment bindings vector to fit. After setting up all the bindings in function declaration instantiation, okay. Now ask declarative environment to do a shrink to fit on its bindings vector. on its vector of bindings. This ends up saving, how much did it save? I already forgot. 12.4 down to 6.8. Right. 6.8, 5.6. Yeah, that's really nice. And now, where else can we do these? Function parameter. Where are you coming from? Parse formal parameters. Maybe we can just go there and like, what if we just go in the parser? Parse formal parameters. What if we just slap a shrink to fit there? Like at the end, before we return the parameters. Boom, shrink to fit. Okay. Statements. What are these? Parse statement list. Scope node append. Oh, interesting. It's calling an API on scope node to append to the list. Scope node append. So parse statement list. Output node append. Oh, I guess output node is the scope node. Okay, well, what if at the very end here we would do like output node dot shrink to fit. And shrink to fit, shrink footit would just shrink to fit on this guy because we're done parsing it. Does it have anything else? It had a bunch of others. Yeah, it has these also. Let's get all of those fellas up in here. Let's shrink to fit all the things. Now that we have a hammer, let's hammer things. Who else can we hammer? Object property. Where you come from? Parse object expression. Parser, parse object expression. Blah, blah, blah. Where are the object properties? Is there a vector of something here somewhere? I guess it's this fella, properties. So where does it bottom out? At the end, move properties. Cool. Not before I shrink to fit. Boom. Okay. Vector of expressions. Can we shrink to fit that? Parse expression. Is there a vector here somewhere? Dun, 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 dun. Here. It's probably this one. Oh, it's for sequence expressions with the comma operator, which is very common in minified JavaScript. So we can easily shrink to fit that sucker right here. No need to get fancy. Variable declarator. This is from parse variable declaration. I'm just going to shrink to fit all the things. So if you think I'm not going to do it, I am going to do it. Where does it end? Here. Declaration. Move declarations. But not before I, you guessed it, shrink to fit. Ha. I wonder if this is going to like be more profitable than everything I spent the first part of the video doing. Let's see. Declaration being appended in add var scope declaration. That's adding to scope node though. So I think that's already covered by our shrink to fit that we did for all the scope node members. Refputter expression, parse array expression. Let's have a look. Vector of refputter to expression. You guessed it. Element, shrink to fit. All right. What are you? Oh, this is regex bytecode. Ignoring that. Switch cases. Okay, well now we're getting a little bit desperate here, like looking at 32 kilobytes. It's time to chill out. We don't have to go after every one of these things. That was quite a bit though. So let's see, how does this all pan out if we actually build and run here? Starting to accumulate a lot of these heap track windows. It would be cool if heap track could show you sort of a delta between two runs. Maybe it does, I don't know. But here goes. The moment of truth. How much can we get with all that shrinking to fitting? Ah, come on, don't be difficult with the... My home internet is difficult sometimes. It usually doesn't fail me while I'm recording, but sometimes. I have once or twice had to stop recording a video because I lost internet access while I was working on some browser thing, which was annoying. Okay. Give me that client event thing, please. There we go. Click. Okay, so we started at 236.9 megs. Hit me. 210. Ooh, 210.2. 236.9 down to 210.2. That means if we take these numbers at face value, that is a reduction of 26.7 megabytes total today, putting us above 10%. Pretty sick. So this was the first one. Let's see where we are in the bottom of here. Leaked. Still have all the vector storages at the top, but if we compare to the first snapshot, we started with 44.9 megs in vector storage, and we are now at 25.9. So we have definitely made a dent in the amount of vector storage. Yeah, so what do we see here? Try append. Yeah, this is shrink to fit right here. Yeah, it makes sense. And then sometimes you're still going to see try grow, because I guess when we did a shrink to fit, then it didn't need to reallocate. So then you see the allocation under regular grow instead. And this stuff could definitely be better. Like if we could pre-compute in some smart way how many bindings we're going to need, then we wouldn't need to first grow and then shrink. It would be less work, but one thing at a time. Declaration, yeah, we got those. Shrinking and fitting, very, very good. Object storage, still pretty chunky. We are still appending to those, but I think it's less straightforward to optimize those, because when it comes to object storage, like, you don't know beforehand how many properties a script is about to add to an object, right? Like if an object says a.foo or o.foo is 1, o.bar is 2, o.baz is 3. You don't know what's coming. Like, are there more properties coming? So it's more risky to try to shrink to fit in a scenario like that. And we probably want to keep a bit of padding when it comes to JavaScript object property storage. So those are less, I would say, less attractive to try to mess with. Just because if you do shrink to fit on every property definition, then you potentially add a huge amount of slowdown because you keep shrinking to fit all the time. Whereas the ones that we went after now were parse time. So like, you only parse the program once, then you can spend the extra moment to shrink to fit your things so that they end up consuming less memory over the long lifetime that they're about to have. Cool. yeah, so yeah, we didn't quite get 100 megs today, but we got 26.7. I think that's still pretty respectable. So let me just go ahead and, oh man, this formatting changes are so weird. Shrink to fit, shrink to fit, shrink to fit. Just a bunch of shrink to fit everywhere. Lib.js. Call shrink to fit on various vectors after parser. Various vectors created during parse. Yeah, vectors that hang around, that stick around in the AST. We're using a lot. We're wasting a fair bit of memory due to the growth padding we add by default. Growth padding we keep by default. When we're, this patch goes after some of these vectors with the shrink to fit stick, and to reduce waste. Yeah, that's pretty good. That's pretty good. Since the AST stays around for a long time, since the AST can stay around for a long time, it seems worth going to some, or it seems worth making it. It is worth making an effort to shrink it down a bit. To shrink it down when we have a chance. Yes. I should probably, no, it's all good. It's all good. Okay, I'm getting a little bit tired. So I think we're gonna wrap it up here. If you made it this far, then thank you for watching, for hanging out, and for bearing with me while I go through this type of activity, which I find really, really fun. It's really rewarding, and obviously, you know, cutting down memory usage is very, very valuable, and something that we want to go after. I don't think that we introduced any unreasonable complexity today. The call expression changes, they were a little bit of complexity, but I feel like the, what was it, like 7 something megabytes of savings made it justified. So I think that's okay. Although if somebody has an idea for how we could sort of turn that pattern into a template or something like that, that would be very interesting. So like a repackageable template that, so you could do the same kind of trick with the custom allocation size and the properties at the tail. That would be very interesting. But I don't have something that would make the code like not worse. It would need to be nicer code. That would be the point of it. Anyways, 26 something megs. I'm happy with that. Hope you liked it, saw something interesting, etc. Hope you maybe even saw some interesting techniques that you can apply to your programs. Although always make sure that you measure first so that you go after the targets that actually matter. If you don't measure like we were doing here, it's super easy to go after irrelevant things. I've wasted countless hours going after pointless optimizations like this myself. So definitely measure so you know that you're doing stuff that really matters. Anyways, thanks for hanging out. See you all next time. Bye.